Welcome to the Unit 9 guided practice. Go ahead and jump into solutions. It says define the terms below: solute, solvent, polar, nonpolar, and intermolecular force. Now, a solute is what is being dissolved. It's the solid normally put into a liquid, but it can be essentially it's just the substance that's in the least amount. A solvent tends to be the liquid. We usually think of water as the solvent, but it is what is doing the dissolving. Polar is talking about a substance that is not sharing the electrons equally, and so therefore it creates a positive and a negative pole. Nonpolar would be sharing the electrons equally, and it doesn't have a positive or a negative pole. It's just neutral. And then an intermolecular force is the attraction between molecules. So this is not the chemical bonds that are holding a molecule together. It's the attraction from one molecule to another. B, what determines if a solute will dissolve in a solvent? Remember that like dissolves like, and so therefore polar will dissolve polar and nonpolar will dissolve nonpolar. Choose a suitable solvent for potassium bromide, then draw the molecular level diagram showing the dissolving of potassium bromide. So we have potassium bromide, your K, B, R, and it is polar because it's ionic. So this is going to be the positive end, this is going to be the negative end. And when they dissociate into water, the potassiums will be surrounded, since it's positive, it will be surrounded by the negative end of the water molecule. So it would look something like this. And all the negative ends of the water molecule, since water is also polar, would end up right next to the potassium, and it would look somewhat like this. And then our bromine would just be the opposite. So the positive ends of the water molecule would be surrounding the negative bromine. Moving on to concentration. This is what is the difference between molarity and molality, and what is the advantage of each. So molarity is defined by concentration, it's moles over liters. And molality is also concentration, but it's defined as moles over kilograms. The advantage of each: moles over liters. When we're talking about this, usually we're talking about aqueous substances, and it has its advantage because we can look at it on the volume and we can actually see it in a graduated cylinder. Molality is moles over kilograms of our solvent, and so therefore we can use this with gases because the gas's volume will change rapidly, and so since it can change, we need something that won't change, and so we use kilograms there. What is the molarity of a solution when 10 grams of our lithium cyanide is dissolved in 480 liters of water? And so molarity is moles, so our molarity equals moles all over liters. So I need moles and I need liters. Well, I have grams, and so what I need to do is convert that to moles. So 10 grams of our lithium cyanide, and we know that lithium cyanide is going to have a molar mass of 32.95 grams in 1 mole. And when we calculate this out, we will get a mole amount of 0.303 moles. And then that is just all over liters. And so this unit is in milliliters. So to get it to liters, we just divide by 1,000, and we get 0.480 liters. And we'll get a molarity of 0.632 molar. On this next one, you're working backwards. So you have the molarity. You're going to use this equation, and essentially what you're going to do is work backwards. So you're going to have your molarity, you have your volume, you're going to find moles, and then you're going to convert from moles to gram using the molar mass. The answer that you should get for C is 16.42 grams, or 41 grams. Now looking at a dilution, it says, how can you tell the difference between concentrated solution and a dilute solution of Kool-Aid? Well, a concentrated solution is going to have a much darker color, a deeper color, and then a dilute solution of Kool-Aid is just going to be lighter. B, what is the molarity of a solution when 200 milliliters of 0.5 molar hydrochloric acid has 300 milliliters of distilled water added to it? So our dilution equation is M1V1 equals M2V2. And here, all we got to do is just make sure that our volumes are going to be the same. And so what we will get, meaning same unit, we have 200 milliliters is our volume. And it has a molarity of 0.5 molar. So there's our M1, our V1. And what we're doing, we have 300 milliliters was added to it. So when we take our 300 milliliters, we added 300 milliliters to it. So that means that our second volume, since we have this, is going to be 500 milliliters, because we're going to have 500 milliliters when we're finished with it. And so what we do is we take our 0.5 times 200 all divided by 500, and we will get a 0.2 molar solution. It says C is what is the volume of water needed to dilute 250 milliliters of a 0.25 molar sodium hydroxide into a 0.10 molar sodium hydroxide. And so we're going to use the same equation, and what we should end up getting here is we should get a new volume of 625 milliliters. Colligative properties, and so when we're looking at this, it says define colligative properties and give 3 examples of them. A colligative property is what happens when a solute is added to a solution. An example of these would be boiling point elevation, freezing point depression, and vapor pressure lowering. Those would be examples of those. B, it says draw a diagram of how sodium chloride can affect the intermolecular attraction between water molecules. So sodium chloride, again, sodium chloride's polar. So this is positive and negative, and what we will see is, again, sodium's positive, and so you're going to have the negative end of the water molecule attaching to it. And so since this gives order to the water molecules, it creates this intermolecular attraction, and basically it makes it harder, or more energy has to be put into solution to take the solution to boil. And so you have to put more energy in to make it boil. You have to lose more energy to make it freeze. Looking at C, it says what is the mass of sodium chloride would be needed to depress the freezing point of 10 kilograms of water by 8 degrees. And so when we're looking at this, we're going to bring it down or lower it by 8 degrees. And so what we will have is the equation that we're going to be using is delta T equals, and this is the change in temperature, so that's going to be our 8. Our I value, which is our, basically when we're looking at it, it's the ions in the water. And then our Kf, which is our constant, our freezing point depression constant. And then we have our lowercase m, which is molality. And so first we're going to solve for molality, and then we're going to solve for mass. So we want to depress this by 8 degrees. Since it's sodium, sodium's going to break up into a sodium ion and a chlorine ion, so it's 2 ions. And our Kf value for water is 1.86. Solving for molality, we get a molality of 2.15 for a molality. Well, molality is going to be moles all over kilograms. Well, we have 10 kilograms of our water, and so therefore 10 times 2.15 gives us 21.5 moles of solute that needs to be added to that water. And then all we do is we take that 21.5 moles, multiply it by the molar mass of sodium, and we get 1,256 grams of sodium chloride that needs to be added. Looking at the solubility of gases and solids, it says how can you increase the solubility of a gas? You do that by lowering the temperature. How can you increase the solubility of a solid? You do that by raising the temperature. And lastly, which of the following has the greatest solubility at 20 degrees Celsius? So we look at the graph. Here's 20 degrees. We go up. And it's going to be our potassium iodide has the greatest solubility. Moving on, looking at equilibrium constants, looking at KSP and equilibrium. When we're doing this, it says write the equilibrium expression of the dissolution of barium phosphate. So barium phosphate is Ba3 PO4 2. And so when it dissociates into 3 of our barium ions and 2 of our phosphate ions. And so what we're going to do is take these guys and take this equation and write our KSP expression. So we take our KSP, which our KSP doesn't include the solid, and this guy's a solid over here, so it just includes this guy over here. So what we're going to have is we're going to have our barium, concentration of our barium ions raised to the third power, and our phosphate, PO4, -3, raised to the second power. On this next one, now what you're going to do is you're going to use the KSP expression of our copper 1 bromide. Write your KSP expression, and in your KSP expression it's going to end up looking, since they have the same, it's a 1-to-1 ratio, you're going to have your KSP, and since you don't know their concentrations, you just label them as X, and since they dissociate the same amount, it'll be X and X, and go ahead and solve for X in that scenario. In C, you're going to do the exact same thing, and let's go ahead and work this one out. So it's calcium fluoride, which dissociates into 2 fluorine ions and 1 calcium ion. So our KSP expression is going to be our calcium and our fluorine ion concentration squared. Now here, since it's completely when it's completely saturated, we can say, well, when it's saturated, this will break up into X, and for every one of the calcium that breaks up, we break up 2X of the fluorine. So we have KSP equals X times 2X squared. Now this can get a little confusing, but 2X squared is going to be 4X squared. So what we get is KSP equaling X times 4X squared, which will give us a KSP equaling our 4X cubed. Now what we're going to do for this is plug in this KSP value here and solve for X. We do that by dividing both sides by 4 and taking the cube root, and we get an X value of 3.3 times 10 to the -4th. Now, since that is X, when we're looking for the fluorine ion, remember that that concentration is not X, it's 2X, so our answer is going to be 6.6 times 10 to the -4th molar concentration of fluorine ions. Looking at Beer-Lambert's law, it says what factors can affect the absorption of light in a solution. That would be concentration, which in Beer-Lambert's law, which is A equals A, B, C. We say that concentration can affect it, and also the path length can affect it. So B is our path length. That can affect it as well. B, the next problem, it says what is the absorbance of a 0.015 molar solution that has an absorptivity of 1.8 times 10 to the -3rd, and the light travels through a 1 centimeter path. So we're going to use our equation, A equals A BC. Plug in our values. That's concentration. That's our molar absorptivity. That is our path length. Plug it in, and we should get an answer of 2.7 times 10 to the negative fifth for our absorbance. Now in C, what you're doing is you're going to do the exact same thing that we just did, except you're going to solve for a different value. You're going to solve for A. So you have your absorbance here, you have your path length of 2, and you have your concentration of 1.0 times 10 to the sixth. And so what you're going to do is take A equals ABC, and you're going to solve for A, which that is going to be A all over BC. When you do that, you should get an answer of 175,000 for your answer.